Hello? Okay. So hopefully people on Zoom did not miss much. So what I was saying is that when the hydrogen in the core is depleted, then the star starts contracting because there is nothing to balance the gravitational flow. And because of that, as the star contracts, it heats up, and that leads to the fusion of helium at the core. And this process continues until we reach iron core. The core is made up of iron, and iron is the most stable element in the periodic table. That means the binding energy per nucleon is more than any other element. So after iron core is formed at the core, we cannot release energy by nuclear fusion. Because of that, when the contraction of the iron core starts, there's nothing to stop it. And the core starts collapsing. Now, the way the core collapses is that the inner part of the core undergoes a homologous infall. What that means is that the inner part of the core shrinks as one object with the infall velocity proportional to radius, as you can see here. And the size of the inner core is quite universal. The outer part of the core is not aware of what is happening inside. So when the inner part of the core reaches nuclear densities, the infall just stops, and the outer part of the core slams into the inner part of the core. The result is that there is a bounce. So just as if we take this heavy object, and when it hits a rigid object, it will bounce back, creating a shock wave. And that is exactly what happens. We have a loud bang, and that is called a shock wave. And that is created because a part of the inner core bounces back with a velocity which is in the radially outward direction, while the outer part of the core is still infalling. So there is a discontinuity in the velocity profile. And this is called a shock wave. And this shock wave propagates outwards. And this shock wave is supposed to blow up the outer part of the envelope. And this is what is called a supernova. But when the numerical simulations of this stellar collapse and the subsequent supernova was done, it was realized that when the shock wave propagates through the outer part of the core, the shock wave just disintegrates iron nuclei, and in the process loses energy, and because of which supernova cannot happen. Now, one thing that was realized that when it comes to these supernovae, 99% of energy is released in the form of neutrinos. So the question is, can we use neutrinos to revive this shock? Now, before we go further, let me explain what a neutrino is. Neutrino is a neutral partner of the charged leptons, and there are three types of neutrinos: electron neutrino, muon neutrino, and tau neutrino. So what Bethe and Wilson proposed is that if a small fraction of this neutrino energy is deposited at the right time, at the right place, then this can lead to hydrodynamical instabilities, which will revive the shock and make the supernova blow up. So this is a cartoon of what we are talking about. So here we have a shock which has stalled, and this is called the gain region. And in the gain region, what happens is the neutrinos which were emitted from this protoneutron star, they deposit a bit of energy, and this leads to hydrodynamical instabilities which will blow up the star. So how much energy is deposited by neutrinos in this gain region? Now that will depend on several factors. One is the number of neutrinos emitted. Second is the energy of the neutrinos, because the cross section of neutrinos increases with energy. So if we have more energetic neutrinos, more energy will be deposited. And also it depends on flavor. Because if we look at reactions of this form, then these reactions cannot happen if we replace this electron neutrino by a muon neutrino, because then we'll have to replace this electron by a muon. And the energy of the neutrinos in supernovae is not sufficient to create muons. So because of this, there are these kind of reactions which only happens for electron type neutrinos, and this leads to flavor dependence of the cross section or the energy deposition. So how many neutrinos are emitted? So this is a plot of the luminosity of the neutrinos emitted as a function of time. This is a simplified figure. So as we can see in the early periods, only electron neutrinos are emitted. And later, all neutrinos are emitted with almost same luminosity within the order of magnitude. So these numbers, 10 power 52, 53 ergs per second, are so large that it's very difficult for us to comprehend what these are. So I'm written here the total luminosity of the sun and the neutrino luminosity of the sun, just for comparison. And you can see that we are more than 20 orders of magnitude above the neutrino luminosity of the sun. So how are these neutrinos produced? So in the first few tens of milliseconds, what happens is that when you have this collapse happening, the electrons combine with protons and in the process emit an electron neutrino. And that is why in the first few tens of milliseconds, you only have electron type neutrinos. But at later stages, what happens is that there are thermal processes which come into picture. And these thermal neutrinos are basically what lead to this deposition of energy and revival of shock, because the neutronization burst happens quite early. So these are a few examples of the thermal processes which we are talking about, which which are mostly responsible for emission of neutrinos. So second point, what is the energy of the neutrinos? So if we look at the interior of this core collapse supernova, the density is so large that the neutrinos are not free streaming. They are trapped. They are undergoing a random walk. So they are in thermal equilibrium with the medium. So the energy of the neutrino at a particular location is determined by the temperature in that location. But they are just sitting there. The energy of the neutrino which is emitted is determined by the temperature at which the density is low enough that they start free streaming. And that happens at few tens of MeVs. In a region called the neutrinosphere, and which is few tens of kilometers in diameter. Okay. So the average energy of neutrinos is few tens of MeVs for all flavors, but it's not the same. And also the radius at which decoupling happens is not the same for all neutrinos. And the reason again is that we can have these kind of reactions for electron neutrinos and electron antineutrinos, which cannot happen for muon neutrinos and tau neutrinos. And if we look at the cross section, then for non-electron neutrinos, the cross section is the least. So they decouple first in the region where the temperature is the largest, and so they have a larger average energy than electron neutrino and electron antineutrino. Electron neutrinos have the lowest energy because we are in a neutron-rich environment, so this reaction happens more than this reaction. So how do we know that this is correct? The reason why we know this is correct is because we've already seen these neutrinos. On 23rd of February 1987, these three reactors in total observed around 25 neutrinos. And shortly afterwards, in the Large Magellanic Cloud, we saw a supernova go off. So this is a picture of the progenitor here, this small star. After a few months, it became something like this. So just imagine the kind of increase in the brightness that has happened. But this brightness, this luminosity in the optical range is a very small fraction of the energy emitted by the supernova. Most of it is emitted in the form of neutrinos. So apart from looking at the energy of the neutrinos helping us in the supernova dynamics, what else can we talk about? And the next thing that where neutrinos are important is R process nucleosynthesis. So let me explain what I mean by R process nucleosynthesis. As I was mentioning before, if we look at iron, it is the most stable element in terms of binding energy per nucleon. So we cannot form elements which are heavier than iron in stars by hydrogen fusion or nuclear fusion, sorry. So how do elements which are much heavier like gold, platinum, silver, etc. are formed? Some of these elements are formed by a process called rapid neutron capture. And in short, it's R process. And neutrinos affect the R process nucleosynthesis. So let us look at what I mean by rapid neutron capture. So let us look at this. Let us start with this element here. So the y-axis here is the element name, and the x-axis is the number of neutrons. So if we start with this element with the star here, and we want to create neodymium 148, how do we create it? See, if this element absorbs a neutron, it will undergo a beta reaction, a beta decay, and end up here. This diagonal line represents the beta decay. So we can never form this 148 if the neutron capture rate is comparable with the rate of beta decay. So we want to capture a lot of neutrons before a beta decay can happen. So we have to absorb like 6 or 7 neutrons, and then it can undergo a beta decay, and we end up with this neodymium 148. So if this is to happen, we need to be in an environment which is very neutron rich. Now, the reason why neutrinos are important is because the ratio of neutrons to protons is governed by how many neutrinos are present in this environment. Because if we have a lot of electron neutrinos, they will destroy the neutrons present there by this reaction. On the other hand, if we have a lot of electron antineutrinos, they will create neutrons. So not only we need to know how many electron neutrinos and electron antineutrinos are present, we also need to know their energy. And this is where neutrinos play a role. Now, throughout this talk until now, I've just talked about neutrino flavor. But neutrino flavor is not conserved. You might have heard of this phenomenon called neutrino oscillations or neutrino flavor transformations. So what that means is that if we start with a neutrino of a particular flavor, it can change its flavor after it propagates. And on top of that, the neutrino flavor oscillation, the rate at which this happens, depends on the medium in which we are studying this phenomenon. Because neutrinos experience refraction or coherent forward scattering due to matter and other neutrinos in the medium. And this modifies the rate at which neutrino oscillations happen. And this has to be taken into account, especially in the dense environments like core collapse supernovae, because the neutrino number density is so large that the neutrino refraction due to other neutrinos cannot be ignored. So before we go forward, let us just make sure that we are on the same page as far as neutrino flavor oscillations are concerned. So this is the equation, the Schrodinger equation, which governs the neutrino flavor evolution. So this is the wave function of electron neutrino and muon neutrino. I have ignored the tau neutrino just for simplicity, just to make the equation simple. And if we know the Hamiltonian, then we can calculate the probability amplitude of finding an electron neutrino or muon neutrino. Now, if we are in the vacuum, this Hamiltonian has quite a simple form. It is this 2 by 2 matrix, which depends on only two parameters: the vacuum frequency, which is related to mass square difference, and the energy. And it is also dependent on the vacuum mixing angle. But if we are in matter, then the things change a bit. So let us see why this is happening. The equation I showed in the previous slide, what it tells us is that if we have a neutrino wave function at a particular time, what the wave function will look like at some later time, t plus delta t. So this red box tells you the amplitude of survival, probability amplitude of survival for electron neutrinos. Now, and that is dependent on the Hamiltonian. So in the previous slide, I just showed what the Hamiltonian contribution is due to just vacuum effects. Now, if we look at the Hamiltonian in the presence of matter, we get an additional contribution, which is proportional to the number density of electrons. So we have to add this term. Now, why do we have to add this term? Where is this coming from? In order to understand that, let us look at this cartoon. So let us look at this electron neutrino wavefront, a plane wave of electron neutrinos traveling from left to right. And it encounters a bunch of electrons here. Now, just for simplicity, I have put them in a straight line. They don't have to be in a straight line. But these are basically a thermal bath of electrons. And when this electron neutrino wavefront hits this gas of electrons, we don't know which electron will be responsible for scattering. So all electrons are equally responsible. So all electrons will interact with the neutrino and lead to a scattered wavefront. So in order to figure out what happened to this wavefront, which originated here, we have to add the amplitude from the scattering from all electrons. And if we add all of them together, we have a constructive interference in the forward direction. And the result is again a plane wave. Now you will say, okay, we started with a plane wave, we ended up with a plane wave. So why should we care about this? The reason we care about this is because this scattering, coherent forward scattering, leads to a phase shift. If there was no coherent forward scattering, we would have this dark green line. But because of the coherent forward scattering, we have this magenta line. So there was a phase shift. And this phase shift is not the same for electron neutrinos and muon neutrinos, because these reactions we are talking about, the charge current interactions, cannot happen for muon neutrinos. So there's more potential experienced by electron neutrinos than muon neutrinos. And because of that, we see interference between the vacuum term and the matter term, and that modifies the oscillation probability. So this is something that is well known. Probably you've studied this in your graduate courses, but this is not all. When we look at core collapse supernovae, the interior of core collapse supernovae are so dense in the neutrinos themselves that neutrinos can experience a similar effect due to other neutrinos. But things become more complicated there. This is the Hamiltonian for the interaction of this is the Hamiltonian which tells us about the coherent forward scattering of neutrinos due to other neutrinos. This rho here is the density matrix of the neutrinos in the medium. And as you can see that this density matrix is evolving with time. So the background is no longer static. It is dynamically evolving as neutrinos evolve. So this makes the coherent forward scattering of neutrinos due to other neutrinos a non-linear phenomenon. And that makes it very difficult to calculate. But if we actually do that, we numerically, we find something very interesting. We find that if we take into account these, as they are called, neutrino self-interactions, or the refraction of neutrinos due to other neutrinos, what we see is that the neutrinos of various different momenta evolve in a way in which they are correlated. And hence, there is a generic description associated with this phenomenon called collective neutrino oscillations, because they oscillate in a collective manner. And this has to be taken into account when we talk about neutrino flavor evolution in the interior of core collapse supernovae. So what happens when we take this into account? I was talking about the radius of decoupling and the energy of the neutrinos being determined by the radius at which the decoupling happens. But that was assuming that neutrino flavor is not changing. If we take into account the fact that as the decoupling process occurs, the neutrinos are changing flavor. If we take that into account, then what we see is something very interesting. So this dashed lines, the red and the blue dashed lines, they show a calculation in which the decoupling phenomenon is calculated, assuming there is no flavor evolution. So as you can see here, at very small radius, the neutrino number density is almost constant. That means they are trapped. And at some radius, they will start falling because they have become decoupled. Now, if we include neutrino oscillations in this decoupling phenomenon, then what you see is that the radius of decoupling has changed. And that means that the average energy could also be affected. So these effects of neutrino flavor evolution are not included when we do a simulations of hydrodynamic simulations of core collapse supernovae. And the reason is that as far as the neutrino flavor evolution in this dense environments is concerned, it's a very active field of research, and we don't know how to actually solve this problem. So to conclude, neutrinos play an important role when it comes to the dynamics of core collapse supernovae, and the large number density of neutrinos present in the interior of core collapse supernova can lead to neutrino flavor evolution, which needs to be studied. And also, neutrinos from supernovae can also be a probe for us to understand the dynamics of core collapse supernovae.
Thank you, Shashank. Thank you. Are there questions?
Hello, I have a question about the last plot that you just showed.
Yep.
What are those? Sorry, where's it? What are those vertical lines?
So that is basically the radius of decoupling according to certain criteria. What we say is that we say a decoupling happens when the neutrino flux is sufficiently forward peaked. And we put a criteria for how forward peaked it has to be to call it a decoupling. But the criteria is same for with mixing and without mixing. And as you can see, because of the neutrino mixing, the radius at which they become sufficiently forward peaked, that radius has changed.
There was another question somewhere here.
Victor.
If galactic supernova happens tomorrow, what kind of observables could help us to improve the understanding that we have of the dynamics of the supernova?
Okay. So there are several things. One is the duration, over which, because our current understanding is that the supernova blast should last for around 10 seconds, which we have more or less verified using 1987A. But second thing, what we need to do is get the energy spectra as a function of time to see how the cooling happens and whether these flavor evolution effects are actually present and in which way they are present, because there are many papers saying what will happen due to the energy spectra due to flavor evolution. Many of them disagree with each other. So we will need to figure out how the energy of the neutrinos evolve as a function of time at the moment they are emitted, because you cannot see what is happening inside the core. But the luminosity and the average energy will tell us the role of flavor evolution and how the flavor evolution occurs at the moment of decoupling. Yeah.
Thank you very much for the talk. It was very, very interesting. It was more of a historical question regarding collective neutrino oscillations. How long have we known, how long have we taken them into account, and how much have we advanced in understanding them better?
Okay, so when you are asking the question, how long we have taken them into account, the answer is not even today. If you look at the hydrodynamic simulations of supernovae, they are not included even today. And the reason is because, as I was mentioning, these oscillations are nonlinear in nature. So just understanding the physics of this flavor evolution is quite complicated. But the fact that these collective effects happen was first proposed by Pantaleone in 92 or 93, I forget. But that was in the context of early universe. This field gained popularity in around 2005 or 2006 when the calculation was done in a simplified model called the neutrino bulb model, where very simplifying assumptions were made, like it was assumed that the supernova is perfectly spherically symmetric and the decoupling of all the neutrinos happen at the same radius and it's instantaneous. And because of that, what happened was that the neutrino oscillations were happening at quite late time and at quite large radius. So people said, okay, if it is happening at late times and at large radius, it cannot affect the supernova dynamics. But then about 10 years later or so, people realized, no, that simplified model no longer holds, and we can have a flavor evolution at quite small radius in very high dense regions. So, and that is quite an active field, like where exactly neutrino oscillations happen. That is still not a settled question.
There's maybe one final question online. I'm going to paraphrase it. It's from Sabila Parvin. It's asking, supernova, inside supernova, do flavor transitions still oscillate? So the probabilities are still oscillatory.
From what we've shown in this paper is that the flavor starts transforming in the region of decoupling. So inside the trapping region, we cannot have neutrino oscillations as far as we know.
I think that's probably answers the question. If there is no urgent question, I propose we move on to student talks, and thank you, Shashank, again.